let me see what we're going to do today. Lots of good stuff. All right, so I want to talk about the midterm briefly, just some of the takeaways from that. The midterms were really good, right? People by and large did really well on those. Saw lots of good work. So I want to talk about a few of the things that gave people more trouble, and answer any lingering questions about the midterm. And then I want to talk again about Programming Assignment 1, which posted last week and is due Friday, I believe. So I wanted to just revisit that, address any questions on the homework you just turned in, take a really quick look at the new homework, which is homework 7, and then go on and probably finish talking about induction, which is what we've been working through. And that will probably do it for the induction part of the course, chapter 3 in the text. And then we're probably going to go on to talking about counting, which will be our next unit. So lots of stuff in there. Let me start with the midterm. And let me bring up a copy of it on Canvas. And if you have questions along the way or questions about anything else, just go ahead and ask. All right, so honor statement, everybody got correct, and got their 0 points for that. So question 2 was the set theory question. Pair of sets A and B, and you had to do the union, intersection, complement, list 5 elements in the power set, and tell me how many elements are in the power set. So no real problem here with the union and the intersection. Nobody counted the 5 and the 7 twice, which is good. Intersection, things in common is just 5 and 7. Takeaway, I think everybody got that correct. So start with A, take away everything that you find. Take away everything from B that's also in A. So start with 3, 5, 7, take away the 5, take away the 7, ignore the 1, you're left with just 3. Listing elements of the power set. So the one kind of small detail here is be really careful. The empty set can be represented like this, and it can be represented like that. But the empty set is not this. Right, this set contains one thing. It contains this thing, which is a set. So the number of things in this is 1, so it's not empty. Number of things in this is 0, so that is the empty set. And this is just a shorthand notation we have for a set containing no elements. That's just a notational thing. And then the power set, since B contains 3 things, the power set contains 2 to the 3rd, which is 8. So we have this formula for a finite set S. The number of things in the power set is 2 raised to the number of things in the set itself. So set with 3 elements, power set would have 8. So no real issues that I saw in any of that. All right, so question 3, we were writing propositions and rewriting them. So our original proposition was if S, then R. If it's sunny, then I go for a run. The inverse you get by just negating each of those terms. If not S, then not R. If it's not sunny, then I don't go for a run. The converse, you flip around the hypothesis and conclusion. If I go for a run, then it's sunny. And the contrapositive, you do both. And the takeaway here is that the contrapositive is logically equivalent to the original proposition, whereas these are not logically equivalent. So part A, write the inverse. That would just be if not S, then not R. Contrapositive would be if not R, then not S. And then C said, write the following statement in the language of propositional logic. If it's not sunny or I have a test, then I will not go for a run. So if it's not sunny or I have a test, then I will not go for a run. And you can put parentheses anywhere you want if you think it makes it clearer. But if there's just one implication, usually everything on the left is taken to imply the thing on the right. So that would be an equivalent to the sentence. And then the last statement, S and not T implies R. So if it's sunny and I do not have a test, then I go for a run. That would be that proposition in words. All right, and then question 4. This was our formal proof question. And let me write this down and then switch to my camera. All right, so we're asked to show that this is a valid theorem. Given this, this, and this, we want to conclude that an indirect or direct proof works here. So let's try an indirect first. So step 1, I'm going to conclude not P. That's the negation of the conclusion. Step 2, well, not P or not Q implies R. Well, we're saying not P is true, so this should get us R, right? But we have to do a little bit of work because we can use those things from page 58, 59 of the text. There's nothing in there which says not P and not P or not Q implies R gives us R, okay? But we do have this disjunctive addition which says not P tells us not P or not Q, and that's disjunctive addition, right? And in my head I'm saying, well, I've got not P, and I know that if either of these is true, R should be true. So I should be able to get to R. Well, the formal way you do that is that if not P is true, then not P ORed with that is true. In other words, it's formalizing the idea that if this piece is true, then this whole thing is true. That's what disjunctive addition does. So that gives us not P or not Q, and then we have not P or not Q implies R. That's the hypothesis. And so we can put those together and we can get R, and that's the chain rule of 3 and 2, right? Not P implies that, that implies R. Not P implies R. That puts that together. And then we can do direct reasoning. We have not P, and we know not P implies R, and so that gives us R. That's direct reasoning, 1 and 4. And now we're all set. We've got R, and we've got R implies S. That's a hypothesis. That gives us S. That's direct reasoning. Between 5 and 6, but we also have not S. That's a hypothesis, and that's a contradiction. Therefore, the negation of the conclusion was incorrect, therefore P, which is what we were asked to show. So that's an indirect, and that's a little less work. It's a lot of lines, but we don't have to do a whole lot. other than, you know, be clear about that disjunctive addition. And if you skipped a step here or there, like if you had gone directly from here to there, I took off a few points. But if you were on the right track and you were working in the right spirit, you got credit for it. So let's see what the direct proof looks like. So direct proof, well, you know, these look like they go together pretty nicely. So I'll say R implies S. That's a hypothesis. And I'll say not S, that's a hypothesis. And if R then S, but S is false, that gives us not R. That's just the contrapositive or indirect reasoning of those first two. And most people got there. Well, we have this thing implies R, and we have not R. So let's restate that first thing. Not P or not Q, and I'll put them in parentheses. Implies R. That's a hypothesis. Well, we've got this implies R, and we've got not R. So indirect reasoning tells us not P or not Q. That's indirect reasoning 3 and 4. All right. Well, anytime you see a not and you see things in parentheses being or'd or anded, pull out De Morgan. Right. So not this or this is the same as not P and not Q. That's De Morgan's theorem. And not P is the same as P, and not Q is the same as Q. And that's double negation. It's got some fancier name in the book. And so you can very directly prove P and Q. Our goal is to prove P. Well, that's just conjunctive simplification. If you know that P and Q are both true, you also know P is true. Right? If I know it's sunny and today is Monday, I also know it's sunny. Because I just said it's sunny and today is Monday. So we can state P, that's conjunctive simplification, and that's what we were trying to show. And in most cases, people went with a direct proof and got most of the way here. A number of people got all the way down to P, full credit. Some people got down to P and Q, but then didn't go down to P, so that's a few points off. Some people got these two and tried to put them together, but didn't follow through after that, right? And so you gotta pull De Morgan out. So lots of partial credit here, but in general, people seem to be on the right track, and most of what I saw was logically sound. And that's the real goal, to be able to construct a logically sound argument. And you know, most of these proofs, there's one step. Here it's De Morgan. On the indirect, it was this disjunctive addition. There's usually one step that, you know, is a little bit subtle or tricky. And if you're missing that, that's just a matter of practice, right? But being able to argue logically and state your reasons and so on, that's the main goal. You do need to be very precise about this, though. And so I said in the problem itself, right, you should have a statement number, the statement, and then a reason. And you can't just say indirect reasoning. You have to say, you know, what statements did you use? What propositions went into that indirect reasoning? Right? You're spelling it out for the reader. The other comment was there were still a few cases where I would see, you know, R implies S, that's a hypothesis, not S, that's a hypothesis. And then somebody would write this. R implies S and not S implies not R. That is not part of your proof, okay? It's a true proposition, but you have not proven not R, right? Unless you go on subsequently and you actually write down not R, you can't use this in your proof. This is not a proof of not R. This is a statement of indirect reasoning. It's a true proposition, so you can put it in your proof, but it doesn't do anything for your proof. It does not tell you that not R is true. This and this, taken together, tell you not R is true, and the reason is indirect reasoning. But simply writing this down does not mean that you've included not R as part of your proof. Right? It's a kind of subtle distinction, but these proofs are all about the subtleties. Alright, so I noted that when I saw it, and if you're still not clear on that, go ahead and ask me what that's all about. Alright, and then the even odd number proof, alright, which needed to be proved using propositional logic and definitions of even and odd. So the problem you were asked to show was that if A plus B plus C is odd, then at least one of A, B, C is odd. Okay, if the sum of three integers is odd, then at least one of those integers has to be odd. And you need to be really mindful of you know, trying to be as precise in these proofs as possible. So, you know, I saw things that said, you know, A and B and C is odd. And to somebody who doesn't know what you're trying to do, they're not going to have any way to interpret this, because we use this and symbol to do the conjunction of propositions, and this implies that these are propositions, and anding those gives you a proposition. You're saying this is an odd proposition, which is not what you meant, right? And this can, you know, it's not just word games. This can lead you into all kinds of you know, strange ways of thinking. At least one of A or B or C is odd. All right, what does that mean, at least one of? Even if we replace those with the word or, it's strange. So you know, you're typing up the exam, right? Most of us can type pretty quickly. Don't be afraid to spell things out. Okay, if A plus B plus C is odd, well, that's a mathematical sum. That's well defined. Then at least one of A, B, or C is odd. And we know what that means. Okay, and I gave you a pretty big old hint in here, which was an indirect proof will probably work best here. Okay. And it's a little tricky to do with a direct proof. You can break it down into cases and things like that, but let's just look at an indirect. Okay, so the hypothesis is the sum of A, B, and C is odd. Then at least one of A, B, C is odd. That's the conclusion. Right, so we're trying to prove if P, then Q. So to do an indirect proof, we start by negating the conclusion. Okay, we assume the hypothesis and we assume the negation of the conclusion, and then we argue to a contradiction. And then we say, therefore, the original conclusion must have been true. And it's a contrapositive wrapped in different clothing. So step one, A plus B plus C is odd. That's the hypothesis. Step two, I'm going to say not at least one of A, B, C is odd. That's the negation of the conclusion. So I'm negating the statement that at least one of A, B, and C is odd. All right. So how do we negate that? Let's try to put this in the language of propositional logic. At least one of A, B, or C is odd. Well, that's the same thing as saying A is odd, or B is odd, or C is odd. Okay, that's what our original conclusion is. A is odd, or B is odd, or C is odd. And, you know, if two of them are odd, if three of them are odd, this is still true. This is equivalent to this. So the negation of Q is the negation of this proposition. And how do you negate a bunch of things that are ORed? Use De Morgan's theorem. So this is the same thing as not A is odd and not B is odd and not C is odd. And the negation of A is odd is A is even. And the negation of B is odd is B is even. And the negation of C is odd is C is even. Now, you didn't need to do all of this on your test, okay? But if you're not sure how to negate it, you can go down to these very specific steps and apply De Morgan's theorem and convince yourself that the negation of at least one of these is odd is all of these are even. Okay, and once you see it, it probably makes sense, right? And if you thought of this on your own without doing all of this stuff, that's great, right? So to negate the conclusion is to say, you know, A is even, B is even, and C is even. That's the negation of the conclusion, right? Because this says at least one of them is odd. The opposite of that is none of them are odd, which means all of them are even. All right, so once we have that established, now the proof is pretty straightforward, or at least, you know, similar to the other even-odd proofs we've done. So if A is even, let's use the definition of even and say, you know, A equals 2 times K, where K is an integer. That's the definition of even. And we can do the same thing. B is even, so B is 2 times J. J is an integer. And C is 2 times N, where N is an integer. These cannot all be the same variable. I can't say A equals 2K, B equals 2K, C equals 2K. Why? Because I just said A, B, and C equal to each other. And I'll be proving a very specific subset of this, which is where your three numbers are the same. But just make them each equal to 2 times an integer. And now, add them up. A plus B plus C equals 2 times, you know, this sum of integers, that's algebra. And since A plus B plus C is 2 times an integer, A plus B plus C is even. And that's a contradiction between 1 and 5. All right, therefore, our negated conclusion must be false, and so our conclusion must be true. Therefore, at least one of A, B, or C is odd, QED. So in the original text, these are all in section 3.5. I think digs into all of these kinds of proofs. And we did some homework questions from there, but there's also some solved homework questions I didn't assign, but you can work on those for the proofs like the previous section where it was, you know, P and Q implies not R, comma, P, comma, not R, that kind of thing. For the even-odd problems, I don't know if those are spelled out in the text. They might be in the additional text, which is where the next homework's coming from. But you can also make up problems like this too, right? I mean, just look at even and odd numbers and find some facts about them by playing around with them. For example, the product of three odd numbers is odd. And you can prove that if the product of three numbers is odd, they all have to be odd, right? Just like if the sum is odd, at least one of them has to be, and so on and so forth. All right, and most of the issues I saw in here were proving the hypothesis. So I would see a proof, and at the end of the proof it would say, therefore A plus B plus C is odd. Well, that's your hypothesis, right? That's what you're starting with as known, and you're trying to prove this thing. So if you do a bunch of work and you prove A plus B plus C is odd, that's cool on its own, but it doesn't prove the given problem. If you start off by saying, suppose A is equal to 2k plus 1, well, you've just written something that we don't know is true. If you say something like, A is odd, B is even, C is even, A equals 2k plus 1, B equals 2j, C equals 2m, A plus B plus C equals 2k plus 1 plus 2j plus 2m equals 2 times k plus j plus m plus 1 equals odd, right? And this is not like, precisely meaningful to say that this is equal to odd. You could say this is an odd number. But what have you shown here? You've shown that if, one of these three numbers is odd, then their sum is odd. That's the converse of what you were after. What you wanted to show is if the sum is odd, then at least one of these must be odd. And showing the converse is not the same as showing, the converse of that, because they're not logically equivalent. So this happened a fair amount. What else? Yeah, and the other issue people got into was negating the conclusion incorrectly. So the negation of the conclusion is not that all three of these are. So the conclusion is at least one of these is odd. So negating the conclusion is not that at least one of these is even, right? It's actually that all three of these are even. And if you assume that, just one of these is even, that might not be the negation of the conclusion, right? You could have the same number satisfy this and also that that previous statement. All right, and then question 6 was some number theory stuff, and not a whole lot of issues in here. So the GCD turns out to be 18, and most people got that. It takes 4 or 5 iterations of the algorithm to get down to 54 equals 3 times 18, and most people did that. Give or take math errors. And math errors were just a couple of points. Let's talk about the modular exponentiation. So 2 to the 82 mod 13. So remember, modular exponentiation is not just, multiplying 2 by itself whatever number of times you like. It's a very specific algorithm, which goes like this. 2 to the first is 2. 2 squared is 2 squared, which is 4. And you keep squaring on each line. 2 to the fourth will be this thing squared, which is 16, which is 3. 2 to the eighth will be 3 squared, which is 9. 2 to the 16th will be 9 squared, which is 81, which is 3. Ooh, am I doing this wrong? Yeah, 6 times 13 is 78. So 81 is 3 more than 78. So that's congruent to 3. 2 to the 32nd is 9. 2 to the 64th is 3. And we've got a pattern now, right? So if you showed me the first few of these, you were good. And then you want to note that 82 equals 64 plus 16 plus 2. And so 2 to the 82nd equals 2 to the 64th times 2 to the 16th times 2 squared. And most people got to this. And 2 to the 64th is 3, and 2 to the 16th is 3, and 2 squared is 4. Here's where most of the mistakes happened. A number of people added these together instead of multiplying them, even if they said multiply up here. They added them together and they got 10. And a number of people, for 2 to the second, wrote down 2 instead of 4, even though they had written 2 to the second equals 4 up here. And so they got 3 times 3 times 2 instead of 3 times 3 times 4. Just math errors or typos, right? So 3 times 3 times 4, this is 9 times 4, which is 36, which is 10 more than 26, so this is congruent to 10 modulo 13. So there's your final answer. So there's 2 to the 82. There's 2 to the 82 minus 10, and if you divide by 13, you get a whole number. All right, so not a lot of problems with that. The main causes of large point loss there was not doing this, right? Multiplying 2 by itself until you got to something that was easy to multiply by other things, or doing 2 to the 10th and raising that to the 8th or something like that. It's valid, it can get you the answer, but this is modular exponentiation. And yeah, math errors, I mean, a couple of points, right? So that's not a big deal. In practice, you know, we're not really doing these things by hand unless we're on a desert island. All right, so questions on any of that? All right, let me do another quick pass on PA1. Because I talked about this in the beginning of class on Friday, but that was, you know, like right before the midterm. And I'm not sure everybody was there and so on. So, programming assignment 1. So, just playing around with integers, right? So write a program that basically lets you type in a number, and this should be an integer, and it should be positive. Okay, I didn't say that in here, but should be a positive integer. And basically, give me 4 pieces of information. 1, show me a list of all the factors between 1 and your number minus 1. So all the factors less than your number. Tell me whether the number is prime or not prime, composite. Add up all the factors from 1 to n minus 1. And then report on the mood of the number. So the mood is gotten by comparing the sum of the factors to the number itself. So if the sum is smaller than the number, we say the number's sad. If it's bigger than the number, we say it's happy. If it's equal to the number, we say it's a perfect number. So you print out those 4 things and your program exits. All right. I'd like the program written in C, written by yourself, should compile on the Linux server using GCC, with no switches except LM if you're using square root. And then upload your .c file to Canvas. Okay, so you can pull it down using WinSCP or SFTP, or you can copy and paste the code or whatever, as long as I end up with a C file that I can compile on the Linux server. Oh yeah, mod and mood, interesting. I hadn't thought of that. I don't know if mood is an official term or not. Happy numbers are a definite, or perfect numbers are a definite thing. But when I was a kid, I called them happy and sad based on factors bigger than or less than a number. I think there's other terms for those. All right, and then there's sample code on the server. So let's just run through that. So put in a number, and I'll put in 360. And it's got all these factors. Right, and I don't list 360 as a factor, it's just the numbers from 1 to the number. Since there's more than one factor, it's not prime. Those factors add up to 810, so this is a very happy number, because the sum is way bigger than the number itself. The saddest numbers of all are the primes, because they only have one factor, and so the sum of the factors is 1. And so that's a sad number. And there are a few perfect numbers. 6 is the smallest perfect number. Some of the factors is 6, 1, 2, and 3. So, so you can't just check up to the square root of the number. Okay, you actually need to go up to the number divided by 2, because we want all the factors less than n. But basically, just make yourself a loop. Start from 1, go up to n minus 1, or maybe n over 2. And see if each of those numbers divides your number n. And if it does, go ahead and print it out and add it to your running sum. You don't need to save these in memory. Okay, we're only printing out the factors once. So while you're doing this print, you can be going through that loop and figuring out the factors. And just every time you find a factor, add it to a running sum. When you get out of that loop, you'll have printed all of the factors, print a new line, and then you can just look at the sum. If the sum is 1, the number is prime. If it's bigger than 1, the number is not prime. And then you can compare the sum to the number and tell if it's happy, sad, or perfect. All right, so not a whole lot of code in here. I'm not worried about, syntax errors, running it with command line arguments or putting in, bad numbers or things like that. You can assume that everyone's playing nice here, and just worry about the code itself, right? The main loop. All right, so questions on that? All right, so that's everything there is to know about PA1, basically. All right, questions on homework 6. Again, I'll grade it. We'll talk about it Wednesday, but questions right now on the homework you just turned in. So this was looking at modular equivalents and primes and powers of primes and GCDs. And I think people asked questions about that last week, because I warned you that could be on the midterm. Yeah, you should be able to get away with scanf. I don't think I actually do any error checking in my code. But I didn't specify any error checking. Let's see. Oh, I do error checking. Don't worry about error checking. Yeah, you can just scan F. Um, yeah, yeah, because not everybody in here is in CSE224. So don't worry about error checking. Okay, just assume there's a legal integer being supplied, and run with that. I'm just going to check it to see if it finds factors and primeness and that kind of stuff. All right, so let's take a look at our Canvas page. So up in the top here, there's an additional CSE215 text. This is where your next homework questions come from. So the main textbook we work from doesn't go through number theory in the same way that we've been talking about it. And it doesn't cover recursion in quite the same way. So I have another text up here. It's a good source of problems. And it's never going to load. Oh, there we go. So your homework comes from sections 3.4 and 3.5. And I'm not going to try to get this from here because this is like way too slow. So let me just pull up my local copy. So 3.4 induction. So I want you to work on questions 1, 5, and 6 from 3.4. So use induction to prove this formula about the sum of cubes. Question 5 is a fun question involving factorial. So just remember, n factorial is the product of everything from 1 through n. So 3 factorial, that's the exclamation mark, is 1 times 2 times 3, that's 6. 5 factorial is 1 times 2 times 3 times 4 times 5, that's 120. Okay, it's probably the fastest growing function on most pocket calculators. So fun little formula, if you add up 1 times 1 factorial, 2 times 2 factorial, 3 times 3 factorial, all the way up to n times n factorial, you get the next factorial minus 1. So this is all, you know, quiz box stuff. It's all playing around with equations, formulae, and trying to find different ways to look at them. Okay? And I'd like you to try these and then come to class and ask questions, and we can work through some of them or similar questions and try to get some insights like that. And then question 6, another summation, reciprocals of 2i minus 1, 2i plus 1 adds up to n over 2n plus 1. Why? Who knows? It's just a problem. And then section 3.5, I gave you 3 problems, and I don't think you need to read this to get any extra insights, but there's lots of examples in here, right? This is a fun problem. Sure, this is a multiple of 6. So there's some good tricks in here that you can see examples of, but this is very much like physics problems, right? I can show you how to do one of these problems, and it can make perfect sense to you. And then I give you another problem that seems similar, and it'll look completely different when you get into it, right? That was my physics experience as an undergrad. It takes more and more practice, and eventually, it's not that you've seen this new problem, but you've seen enough problems similar to it that you can take what you know how to do and turn it into something that works on this problem, right? And that, for me, was the key to making physics doable. Just having some kind of kernel of sample problems to draw on. So 3.5, questions 1, 8, and 9. So question 1, prove that this is a multiple of 3 for all integers bigger than or equal to n. You have to use induction. This is really easy to prove using modular arithmetic, right? Break it into 3 cases where n is congruent to 0, 1, or 2, and you can prove that either n plus 1, or n plus 2 is divisible by 3. and then this whole thing is divisible by 3. But try to prove it using induction. Alright, question 8 and 9 are inequalities. Prove n squared is bigger than 4n plus 1 for big N, and prove 2n plus 1 is less than 2n, 2 to the n for big N. Nope. 9 and 8. N factorial is bigger than 2 to the n. And then n squared is bigger than 4n plus 1. I did not assign number 10. All right, and we haven't talked about strong induction. I'll make some comments on it later on today if we have time. But normal mathematical induction, we show that Pn implies Pn plus 1. Strong, we simply assume that P is true for all n less than or equal to, for all values less than or equal to n, and then we try to show that that implies Pn plus 1. And it's a little easier to make proofs together. To put proofs together if you know more hypotheses. So we'll look at an example of that if we have time. All right. So questions on what we've done so far with induction. And we did a number of examples last week. Some with mathematical expressions, some with tiling a floor with L-shaped tiles. We did one on the number of subsets in the power set. So let's do another non-mathy one. Let's look at the odd pi fight. All right. So what is a pie fight? Well, a pie fight is where you get a bunch of people in a room and you hand them each a chocolate cream pie or something, and you throw your pie at someone, and people get pies thrown at them. It's something to do. So an odd pie fight is a pie fight where you have an odd number of people involved. So 3, 5, 7, 103, right? And here's the basic setup. So picture a room. Okay, this would normally be a room in the STEM building, but we're on COVID protocols now. So picture a room, and you have people walking into this room. And as they walk in, somebody hands them a pie. Okay? And they go and they stand somewhere in the room. And then another person walks in and they get a pie. And they stand somewhere else. And so n people have entered the room, okay? And here's how a pie fight works. When I say go, you find the person who is closest to you and you throw your pie at them. Okay? So you throw your pie at whoever is closest to you. Just straight line measurement. And this notion of closest we need to be careful of, because suppose there are two people who are both exactly 2 meters from you. You wouldn't know who to throw your pie at. So we have a rule which says all distances are unique. So you go in and you stand in the room, and somebody will come through and make sure that there's no two people who are the same distance apart as 2 other people. Okay? If that's the case, if there's 2 sets of people who are exactly the same distance apart, one of those people has to move just a millimeter, just to make it a unique distance. Okay? This is just to ensure that this notion of who is closest to you is well defined. There's always exactly one person closest. It might only be a millimeter closer or an angstrom closer, but there is a closest person to you. That's who you're going to throw your pie at. Okay, so so I'm going to give you a proposition. Let P of n be the proposition there is at least one survivor in an n-person pie fight. So P of n is the proposition that if you do a pie fight as I've just described with n people, at least one person will not get hit by a pie. All right, here's the claim. P of n is true for all odd n bigger than or equal to 3. If n equals 2, then those two people would be, you know, they would throw their pie at each other and they would both get hit by a pie. And it's the only possible pie fight for two people, because there's only one other person you can throw your pie at, so they are the closest person to you. And for one person, this doesn't exist, right? We can't really have a pie fight with just one person, because you're not allowed to throw your pie at yourself. You're not allowed to throw it, you know, at the wall. You got to throw it at a person. So the pie fight is only defined for n bigger than or equal to 2. And the proposition, if n is odd, bigger than or equal to 3, then there'll be at least one person who doesn't get hit. There could be more, but there is at least one survivor. And we're going to prove this using mathematical induction, right? It's a perfect setup for it. So how do we do our proof by induction? We need to do 2 steps. Step 1, we have to prove the base case. So we have to prove P of 3 is true. Well, let's just think about it. So send the first person in the room. Let's call them A. Send the person B in the room. Okay? And now send in a third person. Person C. Well, they are going to be either closer to A or closer to B. Okay? Suppose that C is closer to A. Well, then A is also closer to C. They're going to throw their pies at each other. And nobody's going to throw a pie at B. B is going to survive. B might throw at A or C depending on who they're closer to, but B is not going to get hit with a pie. And if instead C had walked in and was standing closer to B, then B and C would throw at each other because they'd be closest to each other, and A is going to survive. So for 3 pies, it's easy to argue all the possibilities and conclude that P of 3 is true. Okay, step 2. Given P of n, prove P of n plus 2. So we're doing a slightly different version of induction here, because we only want to prove this for odd n. So I've proven my base case P of 3. Let's prove if P is true for n, it's also true for n plus 2. Now, if we wanted to do this just by saying, you know, Pn implies Pn plus 1, we can do that, but we need to reformulate this into where the number of pies is 2 times n plus 1, or 2 times n minus 1. And that's a lot of legwork that's going to get us all tangled up. So we're going to use this slightly different version of induction, which is exactly the same. We're going to show that P of 3 is true, and we're going to show Pn implies Pn plus 2, where n is odd and greater than or equal to 3. And then we're going to be able to conclude P of n is true for all n, which are odd and bigger than or equal to 3. And the way this works is exactly the same as when we first started in deduction. If you want to know if this is true for 7, well, we know it's true for 3. If it's true for 3, it's true for 5. If it's true for 5, it's true for 7. We chain rule a few times, and we've proven P of 7. And if you want to do P of 707, right, P of 3 gets you 5, 5 gets you 7, 7 gets you 9. Just keep chain ruling until you get 705, and then P of 705 tells you P of 707. So this is a slightly more general version of induction, but it's exactly the same logic and the same steps. All right, so how do we prove this inductive step? This is the real kind of magic. Okay, given P of n, how do we prove P of n plus 2? So let's take our room, and suppose there's n plus 2 people. And we're given, remember, P of n is true. So we know if there's n people in this room, there'll be at least one survivor. Okay, now take a room with n plus 2 people. Okay, pick the 2 people closest to each other. And let's call them A and B. And we know there is such a pair of people because all the distances are unique. So if we list all the distances between all pairs of people, that's a finite set of numbers. It's a lot of numbers. But it's a finite set of numbers. We just pick the smallest one. That tells us the 2 people who are closest to each other. So let's just suppose that, you know, these are our 2 people who are closest to each other. Okay, we're starting off, we have n plus 2 people. And we have n plus 2 pies. Nobody's thrown a pie yet. The order in which pies get thrown makes no difference. Everyone can throw their pie at the same time, or they can throw them in alphabetical order. It makes no difference, because who you're going to throw your pie at is predetermined by their distance from you. So we're going to play this game out in pieces. First, we're going to let A and B throw their pies. And the person closest to A is B, and the person closest to B is A. All right, so 2 people have thrown pies. 2 pies have been thrown. So now the number of people left in the room who have not thrown a pie is n, and the number of pies to be thrown is n. And there's 2 possibilities. 2 cases. Case 1, someone who's still holding a pie throws that pie at person A or B. In other words, at least one person in here will throw their pie at either A or B. That's a possibility. Because it could be that, you know, there's someone else whose closest person is B. Okay, so before this, let me label this the surviving people. We started off with n plus 2 people who had not been hit. A and B throw their pie at each other, so 2 people have been hit. So we have n people who have not been hit by a pie yet, and we have n pies left to throw. Okay, suppose somebody in the room who still holds a pie to throw, throws it at either A or B. Okay, you still have n people in the room who have not been hit by a pie, but now there's only n minus 1 pies left to throw. Well, if you have 15 pies and 16 people, however you throw them, there's going to be someone who doesn't get hit by a pie, right? This is a simple counting argument, which we'll be doing, you know, later this week. If you have more people than you have pies, and you can only throw your pie at one person, there's at least one person who doesn't get hit. So in case 1, someone survives. Alright, that's the first case. There's a second possibility. The second possibility is that this does not happen. So no one holding a pie throws at A or B. Okay, so we have n people, we have n pies, and none of these surviving n people are going to throw at either A or B. So what happens here? Well, these people, you know, they can walk out of the room and not affect the game. Right? Because we've just, you know, we're arguing the case where nobody's going to throw a pie at them anyway. So they can walk out of the room. And what we have now? We have a room with n people holding n pies. And we know P of n is true, which means that when they throw their pies, someone will survive. And those are the only possible cases. So in either case, P of n plus 2 is true. And so given P of n, we proved P of n plus 2. That was our inductive step. We proved the base case. Therefore, P of n for all odd n bigger than or equal to 3. And you've proven the odd pi phi theorem. Alright, totally different kind of problem from like sum of integers, right? Or postage stamps. There's no real math in here, right? Other than, you know, n plus 2. But this is a perfectly legitimate use of mathematical induction. All right, questions? So I wouldn't ask you to come up with a proof like that on an exam. But it's good to be able to understand it because it's a different kind of argument. But it's the same proof mechanism, mathematical induction, underneath. All right. So let's prove that all horses are brown using mathematical induction. So I'm going to make a proposition. Let P of n be the proposition given any group of n horses, all horses in that group are the same color. And I claim P of n is true for all n bigger than or equal to 1. And I have seen a brown horse, so if all horses are the same color, this, combined with the fact that I've seen a brown horse, will convince us that all horses must be brown. Alright, so we're going to prove this using mathematical induction. In any group of n horses, all those horses are the same color. Okay, well, we need a base case. So what does P of 1 say? It says in any group of one horse, all the horses in that group are the same color. Well, that's certainly true. Right? If I have a grassy field and there's one horse in that field, are all the horses in that field the same color? Yeah, because there's only one horse. Okay, so P of 1 is true. And that's not a trick. That actually is totally valid. Okay, so now we need to prove P of n implies P of n plus 1. All right, well, how are we going to do this? Let's think about a bunch of horses. So, given n plus 1 horses, I'm going to line them up side by side. Okay, so here's going to be, you know, horse 1, horse 2, horse 3, horse n plus 1. We're indexing our horses from 1 because they're not elements of an array. They're horses. So we'll start counting them from 1. So there's my n plus 1 horses. Okay. And remember, P of n is true. Now we know in our hearts P of n is not true. But when we try to prove this inductive step, we are only showing if P of n is true, P of n plus 1 is true. So for the sake of this inductive step, I'm taking as my hypothesis that P of n is true. I'm going to try to prove that, you know, if any group of n horses have the same color, then any group of n plus 1 horses are all the same color. And it's really easy to do. So first, I'm going to just put a fence around these n horses. That's a group of n horses. P of n is true, so these are all the same color as each other. Now I'm going to move my fence and I'm going to put it around these n horses, and all of these are all the same color as each other. Well, what have I just shown? Horse 1 is the same color as horse 2, is the same color as horse 3, is the same color as horse n, is the same color as horse n plus 1. Therefore, all n plus 1 are the same color. Therefore, P of n plus 1 is true. So P of n implies P of n plus 1. Therefore, P of n for all n by mathematical induction. So all horses are the same color. Alright, so what went wrong? Or is this just something we never noticed about horses? So we've spent a few classes using mathematical induction. If we can really use it to show that all the horses are brown, it seems like there's a problem there. So what's the problem? Yeah, all horses are brown. Speculations? Questions? Or maybe induction is broken. That would be a waste of time if we've been talking about something that doesn't actually work. You included n plus 1 in the set that you made. That was n. So I started with n plus 1 horses, right? Because I'm trying to prove p of n plus 1. But I simply broke it into two subsets of n horses each. And then simply used p of n to show that all of these are the same color, all of those are the same color. So yeah, that part is legal. Right, because from here to here, that definitely is n horses, right? It's n plus 1 with 1 removed. So that's another set of n horses. And p of n applies to any set of n horses. So yeah, I broke mathematical induction. Good thing I got tenure, otherwise I'd get in trouble for that. Let's see, if I'm going to think about this practically, technically horses can't be described as n because they are actually all different from each other. They may be horses, but they are different in subtle or obvious ways. Well, this is true, but if you have a group of one horse, right, this is our base case, p of 1, if you have one horse, it's identical to every horse in that set, right? If you have a set of, 5 integers, those have different values from each other. If you have a set of one integer, every integer in that set is identical to every integer in that set. It's a kind of minimalist base case, but it is perfectly valid. P of 1 is absolutely true. Perhaps the minimum should be 2 horses so that it can be proven that there are exceptions. But you can start your base case from anywhere you want, right? And if you can prove something that you don't like, the conclusion of, using a different proof doesn't invalidate that first proof, right? We've got a problem here. We've got a presumably solid proof that all horses are the same color. If we started, with some different situation, then we might not be able to prove this, but that doesn't invalidate this. So then your set was all the same horse. Yeah, so base case of 1, your whole set is just one horse. There's a field with one horse in it. Every horse in that field is the same color. If it's a brown horse, every horse is brown. If it's a gray horse, every horse in that field is gray. But you're getting close to it. The last 3 comments in particular. And this isn't just about horses. This relates to something that we need to pay attention to in general. So if you have something like this, one thing that can be useful is to go through your logic in a particular case, right? And certainly if I have, if I know that any group of 4 horses, forget the ... if I know that for any group of 4 horses they're all the same color, this absolutely proves any group of 5 horses will be the same color. Because there's, my 5 horses, these 4 must all be the same color, these 4 must all be the same color, so all 5 must be the same color, right? Because this horse is the same color as that one, and that one, and that one's the same color as this one. But let's see what happens if we try to do this. If we break down that logic for 2 horses, so here's my 2 horses, H1, H2. And P1 says all of these horses are the same color. And P1 says all of these horses are the same color. But there's nothing that says H1 and H2 are the same color as each other. Now, if I try to prove P of 3, and I know P of 2 is true, then yeah, here's two horses, they're the same color. Here's two horses, they're the same color, so all three have to be the same color. But this doesn't work when n equals 2. Because this argument up here was based on the idea that, you know, for n horses, these n are the same color, these n are the same color, and so they're all the same color. Well, that's assuming that there's some overlap between these n horses and those n horses. But in the case where n equals 2, there is no such overlap. Right? There's a set of 1, there's a set of 1, there's a set of 2, but they don't have any horses in common. So this argument that, you know, this horse is the same color as this, same color as this, same color as this, and this horse is the same color as this, that's assuming this unwritten assumption that, you know, there's some horses in common to this set and this set. And that's only true if n is bigger than 2. So what I actually showed was Pn implies Pn plus 1 for all n bigger than or equal to 2. This proof only works if there's some horses in common to the overlap. But my base case was for n equals 1. So here's what I proved. I proved P of 1, and I proved P of n implies P of n plus 1 for all n bigger than or equal to 2. That's not a proper setup for mathematical induction. To do mathematical induction, what I really need to do if I'm going to use my inductive step for n bigger than or equal to 2, I need to use P of 2 for my base case. Or, if my base case is 1, I have to prove my inductive step for all n bigger than or equal to 1. Because you can't just prove any old random base case that you want. It has to be a base case from which you can build inductively. P of 1 would get us P of 2, P of 2 gets us 3, 3 gets us 4, and so on. Or P of 2 gets us P of 3, P of 3 gets us P of 4, and so on. But our problem was that we proved these things, and we can't build inductively from that. We have P of 1, but P of 1 does not get us P of 2, because we only showed this step for n bigger than or equal to 2. And in fact, P of 1 does not imply P of 2, because P of 2 is false. In a group of 2 horses, those 2 horses do not have to be the same color. So the proof of this is absolutely valid. Nothing wrong with that. The proof of this was absolutely valid. But together, those don't give us P of n for all n. Right? We need to bump up our base case to 2, and we can't prove that base case. If we could, then this logic would prove completely that all horses are the same color. So your choice of base case is critical. And it's why when you write down your inductive step, you always want to include, right, what the conditions are on n. And you want to make sure that your base case bootstarts your induction accordingly. All right, so that's one way that induction can go wrong. All right, so we are out of time. So we'll talk a little more about induction on Wednesday. We'll talk about I want to talk about towers of Hanoi, which we'll come back to later in the course. And I want to talk about strong induction, and then we'll go on to talk about counting. All right, so I will see you next time. Thank you.